what I want to discuss is the effects of magnetospheric particles on the electric field and vice versa, effects of electric field on magnetospheric particles. So the emphasis of this talk will be entirely magnetospheric, and the atmosphere will just be brushed over. I'm going to do this mostly in terms of reviewing model calculations done at Rice. These contain features that have been discussed earlier by a variety of people. They also consider only very large-scale average electric field with no fine structure at all, and they're heavily oversimplified. Some elements of the situation are considered carefully, and others are completely ignored. Sort of overall picture of magnetospheric convection in the ionosphere is shown on this slide. This is looking down on the north polar ionosphere. These hollow arrows, like that one, those represent plasma E cross B drifts. The heavy arrows, like that one, are electric fields. This is the conventional picture. The arrow heads and arrow tails here, 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 and here, those are supposed to be field-aligned Birkeland currents. Okay, the polar cap plasma is convected anti-sunward, presumably because it's connected by field lines, or connected to field lines which are either merged with the solar wind or are in very close contact with the solar wind and are being swept back with the wind. Then there's a return flow at lower latitudes, which is necessary to keep a steady state in the magnetosphere and ionosphere. Now, in trying to make a halfway quantitative theory of this, it's useful to kind of divide the theoretical problem into two parts by drawing a boundary just outside the polar cap, which would be about like that. As I'm going to draw that boundary, just equatorward of these driving Birkeland currents, those are the Birkeland currents that go down at dawn and up at dusk. They're the ones that Axford showed on a slide from Levy, Pekchak, and Cisco, an old slide yesterday. Okay, now what we do is, so that's the time t equals 0 situation. Okay, now what we do is allow the ion sheet to move the way it wants to under the influence of this electric field that it partly generated itself. So we calculate an electric field, move the ion sheet for a minute or two, recalculate the electric field with a new position of the ion sheet, let the ion sheet move again, and so on. Okay. Next slide shows then what happens half an hour later magnetosphere time. Note that the contorted electric field is gone as the ion sheet is moved, distorted in such a way as to get rid of the high electric fields that it didn't really want in the first place. So the big fields are gone, particularly at night, where the field has gotten pretty small. Okay, another 2 hours later, same view looks like this. Now, by this time, this alphane layer has become almost stationary, so that's almost a steady state, relaxed situation. The most striking feature here is that there's practically no electric field at all, maybe a total of 2 kilovolts drop across the entire region, I mean maximum, across this region that's earthward of the inner edge of the ion sheet. So this is the shielding effect that Chappell was talking about. After you let things relax, the ring current inner edge of the ring current tends to shield the region earthward of it from the convection electric field. Notice also that the inner edge of the ring current almost touches the magnetopause on the front side. That's a consistent feature in these things. So in this case, there's a partial ring current, essentially, because the ring current is so much further out here than it is here. It's a partial ring current that goes around like this. So it's taking charge from the dawn side and putting it back in the dusk side. That current then has to go back into the ionosphere. So it comes from the ionosphere here, out to here, around here, back to the ionosphere here, and then across the ionosphere from dusk to dawn. That's the partial ring current, the ring current contribution to the. Okay, that's the total ring, including the partial ring current and the ionospheric completion of it. Okay, now that causes the ionosphere to do this has to, compared to what it would have done, has to charge up positive here and negative here to make Pedersen currents carry current from here, from the dusk side to the dawn side, and that's the shielding effect. It charges, to complete the partial ring current, it has to charge up positive here and negative here. The amount by which it does that is almost exactly equal to the original convection electric field. Now the next slide shows again the same situation, this time back in the magnetospheric equatorial plane, and this time including the co-rotation field. So this is the electric field in the, like the rest frame of solar ecliptic coordinates, something like that. Anyway, it includes the Earth's co-rotation field. Now here, in this case, these are electric fields in a non-rotating frame, so these are essentially drift velocities of cold particles, if there are any there. The arrows are the directions of drift. They drift along the equipotentials. Let's see, the last closed, it's tempting to associate the plasma pause with the last closed flow line about the Earth, assuming everything's been steady for a while. In this case, the last closed flow line for cold particles about the Earth is this thing. Okay. Note that if that's the plasma pause, which is not totally clear. However, if that's the plasma pause, note that it hugs this alphane layer, the inner edge of the ion sheet, very closely, except right near noon. We've sort of verified the shielding effect of the inner edge of an ion sheet, that was previously suggested by, I think Carlson and Bloch probably saw it first. I'm not sure about that. It was clearly enunciated by Swift and Vassiliounis. The relaxation times, that is, starting from some arbitrary initial condition, the time it takes for this shielding to take place depends strongly on the conductivity and also on the L shell of the shield. But they range from, in the case I showed, a good bit of the large electric field had disappeared in half an hour. In fact, typical times are maybe 10 minutes for some parts of the night side electric field, that there may be several hours for parts of the day side electric field.